Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to Module 5. As we discussed in the last module, that every electron is like a little magnet. And of course, magnets are those, what we normally call magnets, are those special materials in which lots of electrons want to line up in the same direction, as opposed to non-magnetic material where they're all random. And one of the big developments of the last 10 or 20 years has been this gradual integration of these two different fields of spins, spintronics and magnetics into one big field, see? And one of the important steps in that has been this latest observation in the last decade of what's called the spin torque effect. And that has to do with our spin transfer torques. And the basic experiment then would consist of something like this. So again, let's look at a channel where I've drawn the red channels and the blue channels separately. This, of course, you understand, those channels are physically on top of each other. When I draw them separately, that's just a conceptual thing, that's all, just to see it clearly. And you have a magnet that's downwards, pointing downwards. And let's say we start in the anti-parallel configuration. So this one is the opposite direction. Now, if these are big magnets, then of course we can run current through this, and as we have discussed, the resistance depends on whether they are parallel or anti-parallel. But whatever they are, it will stay that way. So what I mean is, if initially we started out anti-parallel, we'd have a high resistance. And supposing I want to measure the parallel resistance, so you want to turn that thing. Well, what would you do? Well, you would put a magnetic field and turn it. So usually, I mentioned earlier that this effect, that resistance depends on parallel or anti-parallel, has been used to read information written in a hard disk. But now, what has been shown is you can even write information. So what one could do is, in a structure like this, put a negative voltage here so that electrons whose spins are in the direction of this magnet are injected, and they come along here, hit this magnet, and if you had enough of it, they could actually force that thing to turn over. So it could go at some point, it would turn round and look like this. What that means is you could then use this effect then to write information on your disk just as well as read. And this is the kind of thing that is now people are trying to use it for real devices. You see, actually for writing them, there's all these spin transfer torque based memory devices that you can easily look up. Now, one thing I should qualify though, that you can do this writing, only if you're using a nanomagnet rather than a big magnet. In other words, if this is a big magnet, then throwing a few spins here makes no difference really. Because by the time you go a few monolayers into that magnet, all the spins are kind of gone. There's nothing left anymore. So there's no way that you're just scratching the surface. There's no way you can affect the magnet that way. See? But you can turn the magnet though if this magnet happens to be a nanomagnet, which means, let's say, a couple of nanometers. What that means is a few atomic layers. And after that is just any other material. So it could be just some ordinary contact here. That's fine. But what you have here is a little nanomagnet. And now if you have all these blue spins come in here, it will flood this entire region and it will act on the entire magnet. And with enough of it, if the current is big enough, it will turn that magnet. And that is how you could write information. Now, what's interesting is that let's say you have managed to turn it. Now it looks this way. So you say, well, what I'd like to do is turn it back, go the other way. And again, interestingly, what experiments have shown is that you can actually turn it back simply by reversing the polarity of the voltage. So instead of minus and plus, let's say we turn this side positive. So one can think of it this way, that when you have a positive voltage, what it sort of does is it extracts spins, these blue spins, from the channel. So you're extracting spins, blues, and taking it out is kind of almost like injecting reds into it. And again, so with enough of this, what will happen is at some point, this will turn over the other way. So by putting a negative voltage, you can write this so that this magnet has the same direction as this one, but if you want to reverse it, you can put a positive voltage there and turn it back. And these are now experimentally established things that are being used to, used to write information onto magnetic memories. Okay. Now what I'd like to talk a little more about then is how we understand this, how we model this, what kind of currents are needed, and so on. Now with magnets, as I mentioned earlier, magnet is one where lots of electrons have their spins lined up. And as I said earlier, every spin, every electron is like a little magnet whose magnetic moment is mu sub b. Now, when you look at magnets, the way you usually describe magnets or characterize magnets is by a plot that looks something like this. This you probably may recall pictures like this, where you have a magnetic field, that's the external magnetic field, and this axis is the magnetization of the magnet. And once the magnet is in a certain direction, let's say this magnet is here, that's the magnetization. And if it was, or if it is in the other direction, it would be here. And the point is that there is usually this hysteresis. So if it is magnetized in a certain direction, then you have to put a certain amount of magnetic field to get it to turn over. And once it is in this direction, again, you have to change the magnetic field in the opposite direction to get it to turn over. And usually, there is these two parameters that people tell you about the magnet. One is this magnetization, what you might call the saturation magnetization, M sub S. And the other is this magnetic field, the magnetic field that's needed to turn it. And that's what you usually write as HK. Okay. So those are the two quantities that people tell you. And the product of the two, so HK and MS, that is often written as this energy, this KU. And I guess if I'm using MKS units, I should probably put a permeability here, mu 0. This, by the way, these units for magnetic things, unfortunately, there's a wide spread in what people do. So I think, again, Feynman Lectures Volume 2 has a nice discussion of some of this. And he summarizes all the different conventions people use. Now in MKS, I think of H as being in amperes per meter, usually. MS also I think of amperes per meter. And if you want to convert it to Tesla, you multiply it by this permeability, mu 0. And this mu 0 times H has the dimensions of what often people write as B. It has the same dimensions as that in MKS. Unfortunately, again, in CGS, H and B have the same dimensions. So depending on what people are using, it could take a little while to get these things straight. And since this is kind of a side topic for us, I won't go into this in any detail. Again, you can easily search on Google and there are nice Wikipedia pages summarizing some of this, actually. Now, the point I wanted to make is a little bit about is the significance of this saturation magnetization, MSV, that if you have material, if someone tells you that I have a certain MS, from that you can deduce that roughly how many spins are in that magnet. As I said, every little spin is a magnet, and the reason the whole thing is a big magnet is because all the spins are lined up. So the question you could ask is, okay, I have a magnet with this saturation magnetization, and I've got, you tell me the volume of it. How many spins do I have in there? And the answer is something like this. You see, MS is like this magnetization. I multiplied by volume. This V has nothing to do with our usual V, which I've been calling voltage. That's not that. This is volume. So MS times V divided by mu sub B, that basically is the number of spins. In the sense that every elementary spin has this magnetic moment of a Bohr magneton. So again, in MKS units, the way I would think about it is, this is amperes square meter. This is amperes per meter, the saturation magnetization, and this is volume, so you could say meter cubed. Okay? So the point is that this ratio is like dimensionless. So you could view the saturation magnetization then as mu B times the number of spins per unit volume. And what you can easily do is, if you assume that you have like 1 spin per atomic volume, you know the size of the space occupied by an atom. If you could take 1 spin per atomic volume and calculate MS, you'll find you'll get the typical numbers people have in magnets. We'll do that in one of the homework problems. We'll go through the numbers, actually. But this is the point I was trying to make then, that every electron again is basically a magnet, and then when you have real magnets, what it means is you got lots of them, but all lined up, see? And this MS then is a measure of how many spins are involved in your magnet. And good magnets typically have like 1 little magnet per atom, essentially 1 or 2 or something on that order, but for every atomic cell. Okay. Now, HK is a measure of this field that you need to actually switch a magnet. So typically, you see, you'd have you'd need a field of say about 100 Gauss or so. 100 Gauss means again in MKS units that would be like 1/100th of a Tesla. So that is the kind of fields you might need to switch a magnet, see? Now, how do you describe the switching of a magnet? Now, this is where usually again it takes some time to get used to this, and we won't be going into it in any depth in this course, is that there is something called this LLG equation that people use, this Landau-Lifshitz-Gilbert equation. And again, in one of the homeworks, I'll have a simple version of this with which you can see some of the things easily. But the basic idea is this M is a vector that tells you the direction of the magnet. And when you apply a magnetic field, it tends to turn the magnet in the direction of the field. Now, the point is that this H that I've written here, it actually includes 2 types of fields. One is there is an internal field, and then there is the external field. In the sense that in a magnet, the way people think of it is, why have all the spins lined up in a particular direction? Well, it's because it is as if due to all the other spins, there is an effective internal field that wants to keep it that way. And so often people would write this H as being composed of two parts. One part that is hk times mz, which means if the magnet, so this m is like a unit vector, and its z component, z being the preferred direction of the magnet, times hk. So this is like the internal field that keeps all the spins lined up, and then you are applying some external field to it. That is how usually people model this here. And then this is the equation that is widely used to describe the dynamics of the magnet. I guess there's a few other terms here that I've left out. Again, we'll talk about it a little bit, some simplified version in a homework problem. That's not very important to the overall picture at this time. But the point I wanted to make is that yes, you put in an external field, and that is how, and in an external field, you can then see how the magnet will turn. So for example, you could solve this equation assuming that initially m is a vector, let's say pointing in the z direction. Let's say this is the z direction and m is a vector in this direction. And now if I put a magnetic field in the opposite direction, if it is bigger than hk, then at some point what will happen is this thing will turn over and go in that direction. And all that dynamics would be described by this LLG equation if we were to solve it. And what it would show is you need an external field of at least hk in order to make the magnet turn from one side to another. Now the interesting point with spin currents, you see, as I mentioned before, that a few years ago if you had asked someone, how do you turn a magnet? The answer would be by applying an external field. You know, there is an internal field that lines things up, and then if you put an external field, it will make the magnet turn. And as I said, one of the important developments of the last decade is that you can actually have spin current. That is, you could have spins being injected from a contact, spins in a certain direction, and that would actually hit that magnet and make it turn, you see. And this is where, you see, one would still use the same equation. Over the last decade, what people have figured out is how to modify this equation to handle spin currents, magnets that are being turned by spin currents. And what that requires is adding another term to this, which depends on this spin current. But what matters though here is, remember, we are looking at, a magnet is composed of thousands of spins, and this is what describes, say, the dynamics of one typical spin in there. You see, this is one. And what is important is the spin current per spin comprising the magnet. So divided by ns. Ns is, let's say the magnet has 1,000,000 spins in it, and you're hitting it with a certain spin current. What is important is how much current do you have per spin in the magnet. And I should divide it by Q if I have, you see, spin current. Question is, how do you define it? That's where, in terms of the units of spin, there are many possibilities. I could say, well, spin current is just how many electrons are coming in per second. You got 20 per second. Or you could say, well, I want to know what spin is coming in per second. Then you see, you take 20 and multiply it by something with the dimensions of angular momentum, something like this Planck's constant, for example. Or you could say, no, I just want the equivalent current associated with it so that I can easily add it to regular currents. So I'd say 20 per second and then multiplied by Q. That is kind of like what we did when we talked of spin currents in an earlier module. And that is why I'm dividing it by Q, so that this whole thing here will have the dimensions of per second, which is what it should have because this is also per second. But the important point here that I'm trying to make is that when you turn a magnet, you need a certain magnetic field HK. And so, if you're trying to make it easy to turn a magnet, you'd like materials with low HK. On the other hand, when you're trying to use spin currents to turn a magnet, what matters is not the total spin current, but spin current per unit spin. And so, if you have a big magnet, you'd need a lot of current to turn it. If you have a small magnet, you'd need much less. See, because depending on how many spins you have. So in that sense, I've often used this analogy that turning things with a magnetic field is sort of like an ordinary oven, while this one is more like a microwave. You see, in a microwave, as you know, if you want to heat up 2 cups of coffee, it needs more energy. You see, it takes more time. Because what matters is, again, it's like you're hitting each one individually. So in that sense here, what matters is spin current per spin. And to date, I think, in small magnets, what people find is this current is on the order of hundreds of microamps. And what they're really trying to do is get this even lower. And in one of the homework problems, I'll try to show you the numbers that lead to that number, in that figure of 100 microamps, and what is involved. So, and if that current can be reduced significantly, then I think this whole method of spin torque switching would have a lot more applications. As it is very promising in terms of small things, because the nice thing about spin current is that, you see, when you have a bunch of magnets, if you apply a magnetic field, as I said, just like a conventional oven, it hits everything. And so it is hard to turn one magnet here without turning another one. Whereas when it comes to spin current, it goes surgically to that magnet alone and doesn't switch anything else around it. And so in that sense, it's good when you're trying to make things smaller. And I think it's very likely that, again, in the coming years, you'll see more and more use of spin transfer torques actually to turn magnets.